Hey, what's up, guys? So today I want to also another algorithm series. So I want to discuss quickly derive the standard type complexity of the merge sort and the quicksort. Okay, so I'm not a good guy which know how to write good code, but I think the complexity analysis for these two algorithms is interesting. So let's quickly review. Okay, so I think everyone knows about both is unlocked in. So let me just quickly first quickly introduce the merge sort. So merge sort is introduced by von Neumann, and the idea is that somebody give you an array. Right, let's say length n, and let's for simplicity, let's assume that they're all distinct, but actually maybe no different. And then you choose half, right? You choose you split into two, and you recursive calls. Okay, once you recursive calls, then suppose you already spend time and make these two arrays sorted, then you can just combine. Okay, so this idea is called a divide and conquer in the computer science. Basically, you separate it and you combine it. Let's say this is sorted, and you just combine it. Right, this is simple, right? You can create another array, and so for example, let's say this is 1, 2. This is 1, 2, 5, and then let's say this is 4, 8, 9. Okay, so then you just merge them, so you just get 1, 2, 4, 5, 8, 9. Okay, so you can just use two indices. Okay, and the two indices parallel. If one is greater than it, then you just take the smallest one and just make it. Okay, so this algorithm type complexity is very simple to analysis. Let's define T of n to be the number of steps. To sort. Number of steps to sort a length n array. Okay, from this proof that T of n is 2t n divided by 2 plus big O of n, right? Because you just need a linear. Actually, this is can be written as theta. Okay, so our goal is to prove that T of n 2t n divided by 2 plus O of n is the T of n is big O and log of n. Okay, so this can be proved using a master theorem. So if you are interested, if you haven't seen a proof, that I can post I have proved this. This is not difficult. Basically, it's the master theorem. Okay, so you just compute the log to 2, which is 1, right? So it's the same as the power of this. So you need to add the log n. So this is the first step approach using the master theorem. Okay, let's second approach. Let me just provide a very trivial approach. Okay, I mean, if you are the first time that you see this kind of recursive, then you can just prove by yourself, right? This is not difficult. So let's assume that our algorithm looks like this. Plus some Cn for some C, right? Because if n is large enough, the big O notation means that you can find a C which is bounded. Okay, so let's assume this is true. And let's say T of 2 is 2T of 1 plus 2C. The T of 4 is 2T of 2 plus 4C. Okay, and the T of 8 is 2T of 4 plus AC. Okay, so if you see this, if it's T of 8, you can write it as 2 times 2T of 2 plus 4C plus AC. Okay, and which is 4T of 2 plus AC, which is 4 times 2T of 1 plus 2C plus AC plus AC. Okay, so you get the 8T of 1 plus 16C. Sorry, 24C. Okay, maybe you still don't see the let's write down. Okay, so T of 8 is 2T of 1 plus 24C. Okay, and then you can check that maybe T of 16 just times 2, right? So for T of 1 times 48C plus another 16C. Okay. Okay, I think up to now that you can easily see the you can easily see the see what you can easily see the pattern, right? Okay, so the pattern will be what you can check by yourself, right? Let's say 2 to n is basically 4 times sorry, I'm stupid. This is 8. That's 16, right? So this t of 2 to n will be, you see, this is 8, this is 8, this is 16, this is 16, right? So you can easily use mathematical induction to show the following is true. You can easily see that t of n, t of 2 to the n is 2 to the n times t of 1 plus what? Plus the, for example, this is a times c, right? This is a times 3. This is 16 times 4. Okay, so you can easily check that this is let's say n times 2 to the n c. Okay, so for example, if n is 3, you get 3 times 8, which is 24. Okay, so for 4, t of 4 is 4 of t of 1 plus 4 of t of 1 plus ac. In this case, it's just 2 times 2 to the 2. Okay, so this is our results. Okay, so you just let 2 to n to become n, you get t of n equals to n, right? And now and plus okay, bad notation. Bad notation. Okay, so let's say 2 to n is n tilde. So it means that the t of n tilde is n tilde t of 1 plus n times 2 to n c, which is so n is a log n tilde c plus n tilde t of 1, which is a constant. So we prove that t of n tilde is a big O of n tilde log n tilde, which we transform n tilde to n. So we prove that t of n is a O of n log n. Okay, it's very elementary approach that you don't need to use a master's theorem. Actually, you can prove master's theorem like using this very stupid the algebra way. Okay, so that's another topic is that the analysis of quicksort. Okay, this is interesting. This is more more interesting because there's a randomness. Okay, so the idea of the quicksort. Okay, so if you are interested in the complexity theory, you can check out my another video called discussing so-called BPP, which is a bounded probability, basically complexity class, discussing the which you can solve in the polynomial time if you add the randomness. Okay. So idea is that somebody gives you an array, and you choose a P called a pivot. Okay. So once you choose this pivot, this is step 1. Step 1, you choose pivot, and step 2. Okay. Step 1 is you randomly choose pivot. Okay. Step 2 is you do the so-called partition. So partition means that you separate to something. This one is less or equal to P, and this one greater equal to P. Okay, so basically you separate into 2 parts, or basically, but if you have the same amount of that should put in here, maybe this should be greater. Okay, so less or equal to P, put left hand side, right? Greater than P, put right hand side, and then your recursive call both. Okay, then do a recursive. Recursive on the left and right side. And by definition, that this will works. Okay, you can try to prove. Okay. So the hard part is to prove that the following is that if you given an array. So this is a theorem. This is a theorem that results basically. Let's say somebody gives you array A, and you randomly choose. You randomly perform. Basically, you randomly choose a pivot, and for the next step, you randomly choose another pivot, and keep going, randomly perform quicksort. basically is you randomly choose a pivot, and the average runtime is O log n. Okay, so this analysis is a little bit difficult because there is a randomness. Okay, so let me just make it very rigorous. So the idea is that you first need to choose one pivot, and then you partition into two, and you choose next pivot, and then you partition into partition both left hand and right hand side, and you choose pivot. Okay, so the running time that we want to compute basically is the expectation value. Okay, on something which is, let me just say, in the future, but the expectation value what is the expectation value is a pivot sequence. So this is this is a difficult sum, right? You take all the possible pivot sequence. So you are not randomly choose the initial, but you randomly choose the initial in the next step. And the next step will depend on the randomly initial that you choose. Okay, so this is a pivot sequence and the expectation value of the number of the comparison. Because what you're doing is that you are trying to compare with the two, right? So this all these two methods are basically only using the comparison. Okay, so you can only describe which one is large by using a comparison. Okay, so this is the expectation number of the number of comparisons. Okay, so let's write xij. Okay, and let's write xi, the definition of xij. So xij is a random variable, right? Because I choose a p-bar sequence. So this xiij is defined to be the let's do this. Okay, let's write array A, and let's label it by z. So let's sort it array A and imagine that this is our correct way. So basically z1 less or equal to z2, z2 less or equal to z3, and keep going. Okay, so xij is defined to be the number of comparison. The number of comparison made in a quicksort. Okay, so our goal is to find expectation value of xij, but sum over xij. Sum over all of ij. Okay, but this is just very simple, right? Because let me just, okay, so this is all ij. Technically, we should sum from I to 0 to n minus 1, and j from I plus 1 to n. Okay, the reason is that we already compare pair of it, right? So we don't need to repeatedly compare. Okay, so and the expectation value is linear. So all I can do is just write the following: I from 0 to n, and then j from I plus 1 to n, and the expectation value of this xij. Okay, so this runtime is what we need to compute. Okay, so let me just write down results. Our goal is to compute summation I from 0 to n minus 1, j from I plus 1 to n, expectation value of xij. Okay, and all so expectation value act on all the p-bar sequence. Okay, so compute this fact 1. So fact 1, or you can use lemma. Okay, so fact 1 is that the xij is either 0 or 1. Okay, so this is a reason. This is just provide reason. So reason is simple, right? Because in a quick sort, right? Let's say you choose this as a pivot. So if you choose two numbers, these two numbers will only compare if one of its pivots, right? So if I choose these to be pivots, then I will compare this. And either this one will either put right or left. But once I put it, then then this will fix, right? So no one will try to compare with this one. So once I put right or left, then these two number will not be compared in the future. So reason is that after partition, they will not be compared. They will not be compared in the future. Okay, so it is either 0, 1. So now we can use the standard expectation value of xij is either 0, 1, right? So it's 0 times the probability of xij compared 0 plus 1. That's probability of xij is 1. Okay, so now our expectation value of xij is the probability of xij equals to 1. Okay, so these terms can be written as I from 0 and minus 1, j from I plus 1 expectation value xij, which is this replaced into the probability of xij to be compared. Okay, so lemma 2. So what is the probability of xij equals to 1? Okay, so this is also simple, right? Let's consider zi and zj. And then and then I consider, let's say, zi plus, let's consider all the middle number. Okay, so so as I said that these two numbers will compare if one of these choose to be pivot, right? So if one of it choose to be pivot, it's pivot, then we will compare. Okay. Okay, so once we do this, then there are 3 cases, right? So this is the first case. If I choose a pivot here, then all of these will be put into right and pass into the next iteration. If I do this, then this one will also, if I do this, then the whole red sequence will be posted into the next step. Okay, so we don't need to care about this, right? But if I choose if I choose a pivot to be here, then these two guys will not be compared, right? Because this guy will only compare to this blue point. Okay, so the probability of these two number will be compared will be j minus I plus 1, right? Because this is a total number from I to j, and since it's inclusive, so you need to add 1, and 2, right? 2 is either I or j. Okay, in our case, that there's no way to compare these two. If you choose the number in the middle, that everyone will only compare with the number of the middle, and these two numbers will not be compared. Okay, so our runtime. So let me just our runtime will be the following. Will be the following, as I said. Okay, will be the following is that the expectation value. Let's say, sorry, so I from 0 to n minus 1, j from I plus 1 to n. Expectation value of xij will be the I from 0 to n minus 1, j from I plus 1 to n. The probability of xij equals to 1, which is 2 divided by I plus j equals to 1. Okay, our goal is to finally use your simple analysis tool to compute this, and hopefully you learn the mathematical analysis. Oh, this is trivial, don't worry. This is very simple. Okay, so let's say this is our runtime. This is our runtime. Is I from 0 to minus 1. Okay, so let's write it down, right? So if j is I plus 1, I get, let's say I pull out 2. Okay, j is I plus 1, I get 1 divided by 2, 1 divided by 3, up to minus I plus 1, 1. Okay. Okay, so simple fact that hopefully you learn into your analysis video is that analysis lecture is that if you don't know this, then I will post a link below that you can prove 1 plus 1 over half plus 1 over third 1 over n, right? This is my approach to log n. This is a harmonic series. Okay, actually there is a constant called Euler-Mascherani constant. Okay, so this guy is bounded by 2 times I from 0 to n minus 1 log minus I plus 1, which I can bound this to be 2I from 0 to n minus 1 to log n. Okay, because this log I n minus I plus 1 is less or equal to log n. Okay, so this guy finally is bounded by 2n log n. Okay, so this proves that the runtime is bounded by 2n log n by using the previous theorem. Okay, so finally, I want to say about the lower bounds. Lower bounds of the comparison. comparison, lower bound of the comparison sorting. Okay, this is very trivial. So theorem is that the optimal sorting. So optimal sorting that if you only use the comparison, that is can at most achieve n log n. So basically, it means that the merge sort and the quick sort and as the complexity of view are optimal if you only use the comparison sorting. Okay, so proof just one line. Okay, suppose you want to use a k-step sortings, k-steps comparison. So you only do the k-steps compare. Then you can at most create 2 to the k different results. You can prove this, right? Because you will create a binary search tree or binary tree that you only got 2 to the k results. But you have a number, right? You have n factorial results. So your 2 to the k should compare with the n factorial. Okay, so they should have the same order. Or at least 2 to k should greater or equal to n factorial. Okay, then you take log 2, you get k times k greater or equal to log n factorial. Okay, and then you can use the Stirling formula. If you don't know Stirling formula proof, that I will post the link below so you can check. Okay, so n factorial is square root of 2 pi n divided by n. Okay, so if you take the log n factorial, you don't need to care about square root of 2 pi n because this will this is small compared to n, so it's n log n. So this is n log n. Okay, yeah, so this is I think all the thing I want to talk about sorting. So merge sort analysis, quick sort analysis, and the lower bounds of comparison sorting. That's it. See you guys next videos.